Welcome back. We're moving into our next section, which is virtualization protocols and techniques. Now, this is a vast topic, not so much in this class, but there are certainly tons and tons of things that we can talk about when it comes to virtualization. Virtualizing physical hardware, virtualizing servers and PCs, virtualizing firewalls into different firewall contexts, virtualizing routing tables into different virtual route forwarding instances, and so on. So it is a vast topic. Our objective is to really just kind of talk about some of the high-level points in this particular section, take a look at a couple of exercises as part of the process, and then we'll wrap up for today. Virtualizing, as you guys know, is taking what would traditionally be one physical platform that's performing one function and dividing it up into logical platforms, or one process and dividing it up into logical processes to allow us to either facilitate multiple clients or to provide for some level of redundancy or segmentation of client information and so on. So in this section, we're going to take a look at server virtualization, network virtualization, including things like path isolation with GRE. We don't talk about DMVPN in this case, which also provides path isolation, but with the ability to do point to multi-point as well as hub and spoke and encryption with IPsec. So we'll talk a little bit about GRE, which is a very, very simple concept, just encapsulating data inside of a GRE header and a packet header. And then we're also going to talk about VPN routing and forwarding, which is VRF. That's typically going to be used for things like MPLS or multi-protocol BGP and so on. So let's get started. All right. With server virtualization, we're taking a physical platform and we are virtualizing it into multiple logical platforms. Now, how we decide to do that, whether we're using a type 1 hypervisor or a type 2 hypervisor, will depend on how that virtualization takes place, right? A type 1 hypervisor has access to the physical hardware. A type 2 hypervisor has access to the operating system, and so on. And we differentiate that. This is not typically a Cisco discussion, but we are integrating now the discussion of Cisco UCS, the Unified Communications Server, which is used in a lot of different Cisco applications today, including most of the security applications that we see as well. Standard deployment of applications on computers involves a single operating system that is installed on the computer. To provide the greatest stability in a business environment, good practice dictates that a single type of application should be present on the operating system. Otherwise, compatibility issues could result, and so on. This approach provides good stability, but it's not cost effective, and frankly, it doesn't really scale very well. As the number of applications grow, the number of servers that you need to service those applications, the number of devices you need to service those applications is going to grow significantly as well. The method of server usage that we see, that particular method was Cisco Unified Communications Server 7.x. We actually had the voice media, voice telephony group software, which was basically Cisco Unified Communications Manager. The bare metal servers, which were the MCS 7800 series platforms, they were deployed on this UC. The UC applications were employed on these servers, but we didn't really have the server itself provided only one function, and that function was call routing or call control. We would have another server in the environment that would provide services like unified voicemail or a voicemail application. We might have a call center application, but all these were disparate systems that were configured that were not that were separate and were not combined together in a single platform. So we had this physical server that had some specialized operating system on it, and we were running these applications individually on these servers. All right. The servers themselves had their own CPU, their own memory, their own storage, their own network connections, etc. Virtualization allows us to take that same physical hardware and abstract it into multiple logical systems. And it doesn't have to be just a server platform. It could be a firewall. The Cisco ASA firewalls have the ability to be virtualized into different contexts. It could be a Nexus platform. It could be a router. It could be switches and so on. A virtualized server has a physical hardware platform with various CPUs, various memory, storage, and network components. It usually will typically include some sort of virtual switch internally that allows us to create VLANs and do .1Q tagging and whatnot for the ESXi hosts or the operating systems that are running, what we call the guest OSs that are running on the platform. And then we would simply allocate resources to those platforms in the build when we were deploying the host. And the host would get, some of those CPU resources and some of the memory resources and so on. So we had some hardware that might have been dedicated to that client, but usually it's a pool of hardware that gets assigned to the virtual host. We have our own operating system installed on that guest OS, or that VMware partition, if you will, and then we had the various applications. So the hypervisor, which is essentially that guest operating system, is what gets installed, and it has some sort of lightweight operating system, some other application software. So you might have, instead of one server running Cisco Unified Communications Manager, now you have one server that's running Unity Connection and Unified Communications Manager and UCCX, Contact Center Express, Telepresence Server, all the different type of unified presence server and so on, workforce optimization, whatever. The hypervisor would be used in almost all collaboration applications. The primary hypervisor that Cisco uses is VMware ESXi or vSphere. All right, but there are other vendors that make their own virtualized environments. Microsoft, of course, has their own as well. Virtual machines get created with the software, and then we represent the resources that those virtual machines are allowed to use, the CPU cores, the memory, the hard disk space, the virtual network interface cards that allow us to interact or communicate directly with the physical hardware on the device. And we're pooling all these physical resources to allow multiple virtual machines to have access to these resources. The operating system has access to those assigned resources as if they were physically part of that particular platform, that virtualized platform, but in reality, that's not the case. Obviously, we're limiting what is available to that particular client. All right. So this approach has lots of different benefits. Right. The virtualization layer provides virtualized hardware interfaces to different operating systems. Even if we have different physical servers in a data center that are provided by three different vendors, they appear to have the same basic installation. All right. The virtualized layer is then capable of segmenting that physical hardware, separating those physical resources to give access to those resources, assign those resources to those individual virtual machines. I'm trying to figure out the best way to say that. All right. So we've got guest OSs, we've got guest applications, and we've got a physical server. Now, this is not a server class. It's not a VMware class. And the only reason that we're actually kind of discussing this is because of Cisco's UCS environment, right? Cisco's UCS platform, which is a key component, obviously, to what we're doing in most modern Cisco environments with applications, collaboration applications, and security applications, and so on. So we can allocate resources through the hypervisor, which has access to the hardware. A Windows server running email might require different types of resources than a Linux server running web applications, or a Linux server running maybe a database application, and so on. So we can start to allocate specific amounts of hardware based on the loading conditions and the requirements of each of those operating systems. So they give you an example here. If a host server has 24 CPU cores, two 12-core processors, you could add 24 VMs that need one CPU each. Makes sense, basic math. However, a video conferencing application like Cisco Meeting Server needs 20 virtual CPUs, and other applications may require 2 CPUs each. So in that case, you would only be able to have 3 VMs on that particular host. So again, it's just a matter of allocating resources to the individual clients based on their specific needs. The hypervisor itself is what abstracts or provides that abstraction layer between the operating system and the hardware. VMware ESXi would be your abstraction layer for most Cisco applications, as an example. And it is like a separate operating system, but it has a specific purpose. The specific purpose is to manage the resource allocation to these individual VMs and so on. The abstraction layer supports installing multiple operating systems, which can be different types. You can deploy just about any type of operating system, but the hypervisor only supports virtual machines. It's not intended for installing the actual applications. So the hypervisor allows you to deploy a virtual machine by allocating specific resources to that machine, but it doesn't actually allow you to install the operating system. Cisco Unified Communications applications started working with ESXi 4.0 and Call Manager 8.0, Cisco Unified Communication Manager 8.0, but now they're up to ESXi support for version 5 and beyond. Microsoft, of course, has Hyper-V. Cisco still doesn't support Hyper-V. Citrix has Zen. Red Hat has KVM. And I don't know that there's any roadmap for Cisco to actually support these or not. All right. So again, this is very, very high level. Obviously not a lot of detail. When we get into the actual network virtualization stuff, that's going to be a little bit more interesting. Because again, this is not really the point of this class, is to learn about VMware and ESXi hosts and virtualization technologies. All right, so we'll kind of wrap up this section here, and we'll continue on to get to some of the more interesting sections. So what does the hypervisor actually do? It gives operating systems access to resources on the physical host. And you allocate those resources when you establish the virtual machine. So for example, if I come into my VMware workstation, which I use to run things like Gns3 and ICE and other things. By the way, this VMware workstation software is in that software folder that I gave you guys. That tiny URL link where you downloaded the VCE software. You can get VMware Workstation with a license from there as well, and you're going to need that anyway to install Gns3. So I have this kind of interface, if you will. This is a guest operating system, and I've got resources allocated to this guest operating system that are, getting pulled from my physical resources on my platform. I gave this 8 processors. I have 4 processors with 2 cores each, so I have total of 8 cores. And I gave it 4 gigs of memory. I have 32 gigs of memory. Hard disk space was minimal. If I wanted to attach a virtual drive, network adapter, display adapter, and so on. So that's how I allocate those resources. And then when I power on that machine, it simply boots up like it's a normal operating system. And then I can use a virtual switch that's configured inside to either, in this case, I would bridge it to, I would bridge this to my physical interface to be able to get some public communication or some communication outside of the virtual machine. But that's an option. Let me show you another one here real quick. This one you guys will get a kick out of. Let's see. Let's do this one. Believe it or not, I actually set these up because I thought it would be kind of cool. This is Windows for Workgroups. I don't know if you guys remember that. Some of you are probably way too young to remember that. But yes, this is when Windows was a DOS application. And that's what you would run. That's what Windows used to look like. So I actually installed every version of Windows on my machine, like Windows ME and Windows 98, Windows 95, Windows XP. Got them all. Kind of play around with them. But yeah, this was Windows. This is what it looked like. You had some games. All right, a couple of games there. You had your DOS prompt, so you can do some crazy programming. You had your applications. Yeah, that's it. I mean, you could do some painting if you wanted to do some painting. That's kind of cool, right? Kind of takes you back, doesn't it? So anyway, I guess that does speak to the point that you can pretty much put anything on as a host in VMware. So this one was a little bit more challenging because I actually had to create virtual instances of the floppy disks that loaded DOS, and then I could load Windows on top of that. This is the Gns3 interface, which is basically just a Linux Ubuntu server that's running Gns3. But all right, so you've got applications that sit on top of the operating system, which have interactions with the hardware, and that's essentially what the VM is. It's kind of a combination of all of those things. A virtual machine is a logical container that holds all of the resources that an operating system requires for normal operation, such as graphics adapters, memory, processors, networking, and so on. As far as the operating system goes, there's really no difference because it doesn't matter, right? They're all just sharing physical resources. A VM is the virtual equivalent of a physical PC or a server, so it requires the same set of functions, right? It requires that it has CPUs, it requires that it has memory, and so on. Now, I'm using VMware Workstation, but you can have a VMware server with a vSphere client, and then you can use that vSphere client to deploy multiple VMs within an environment. This is typically what you would see on a Cisco UCS platform. And if some of you are used to dealing with Cisco voice over IP applications, you would see this quite often, right? This is a call manager and an expressway core implementation. So these are individual VMs that have been deployed, and these are all the properties of the VMs, how much memory is allocated, resources, and so on. All right, a vSphere host can be controlled and configured individually or part of a group of hosts. That's where vCenter comes into play. vCenter is a licensed application that allows you to configure and control multiple vSphere clients. You can manage those vSphere clients individually with a free application, or you can use vCenter to manage and deploy those applications, multiple platforms on one server. So this is the actual physical server, and then these are the virtual machines that have been deployed on that server. All right. Actually, these are physical servers, and then these are the virtual machines that have been deployed. Okay. All right. Typically, that would be something you would do in a much larger environment. All right. Now, beyond the fact that you can configure multiple hosts from one interface, you can also activate different features like a virtual distribution switch, load balancing, CPU compatibility. Just get a lot more control when you're running vCenter to manage the VMware machines. Now, I will say this, and I'm not completely versed on it, so I can't speak to it in detail, but there is a way that Cisco handles interaction with VMware clients that is different than the way other vendors handle interaction with VMware clients. And their claim to fame, I remember going through an online class one time where Cisco had an engineer that was much smarter than me, was going through and describing that unique interaction that they've developed that makes Cisco applications much more efficient. I have no idea what it is, but something to that effect. And I'm sure if you Google Cisco and VMware and vSphere, that you might find some documentation on that. Which two software clients can be used to directly connect to an ESXi host server? vSphere client would be one, right? That's what we were talking about previously. Well, actually, are they speaking about the application on the server, or are they speaking about the VMware platform, right? Like I did with VMware Workstation. If it's the application, it could be Call Manager application, Cisco OS administration. Those would be two choices. The only reason I'm hesitating is because vSphere client is that free application that allows you to manage a VMware Workstation or VMware platform independently. But I'm not seeing vCenter here. So I have a feeling that they're speaking of the applications directly on the VMware host. So there you go. All right. So in our next section, we're going to talk about the need for network virtualization. We've spent quite a bit of time over several different sections here talking about how to build an enterprise and how to deliver services within the enterprise. But virtualization provides us the ability, at a minimum from a security standpoint, to logically isolate or partition elements of our network on a physical architecture, if you will. And some of the most common methods of doing virtualization would be just as simple as setting up perhaps a VLAN, or maybe private VLANs, or virtualizing physical hardware into virtual contexts, like an ASA, adaptive security appliance, or a router that provides us the ability to do multi-tenancy, provides us the ability to separate and logically configure different elements in our design. Now, obviously, the goal here would be to logically isolate traffic. It could be for efficiency purposes. You know, we may decide that we're going to be applying different quality of service policies to different types of traffic. Perhaps it's for security purposes where we don't want, you know, one tenant's traffic to be commingled with other tenants' traffic and so on. But the key is that we want that virtualized environment to operate like a traditionally physically separated network. That end user experience should look like they are in a dedicated, connected network. It's going to provide all the confidentiality, the message integrity, the security. It's going to have its own independent service levels, maybe even running our own policies, our own routing protocols, making our own routing decisions, and so on. The virtualized environment should also be very adaptable. It should provide us the ability to turn up services or turn down services or customize services on the fly, if you will, just as easy as if we were modifying dedicated services to a particular client, right? With regard to security, for example, this is going to be possible, this ability to create a secure environment that's specific to a particular group of users based on security zones. And in one of our initial lessons, we talked about how we zone out a network and how we define different security zones, and how those particular security zones are going to be governed by policies that are enforced at a central location. And the policies, of course, because they are security policies, are going to allow us to restrict the kind of data that's going to flow between these different virtual environments. And oftentimes we may decide that nothing is going to flow between these virtual environments, or we may want to leak out specific information or leak out specific connectivity based on these logical partitions and how we communicate across these networks. Now, because these policies are going to be centrally enforced, you know, adding services, adding VPN, adding additional, or turning up, I should say, additional services wouldn't necessarily require a whole kind of reconfiguration of the environment. It would very easily just be turned up based on the fact that we have this infrastructure in place, right? This modular infrastructure. And quite frankly, this is one of the major benefits of cloud computing in general. The ability to turn up or add additional services with minimal downtime and minimal resources required. So the obvious benefit of that, of course, it would be the reduced operational cost, because everybody kind of gets the same services. They may have different operational parameters, but the services can be kind of a la carte, and we can apply different service principles to different networks, right? Based on our policies and simply fine-tuning what we have in our environment. All right, so network virtualization gives us lots and lots of different opportunity to extend services to different business entities, solving different business problems, or maybe even focusing on different business drivers. And these can be for very, very simple, easy to configure networks, or they can be very complex enterprise networks with lots and lots of different resources. All right, so it could be something as simple as maybe providing some guest access, visitors, allowing visitors that are external to your network, at least from a permissions and security standpoint, to access maybe internet resources, but also preventing them from incorrectly, either maliciously or non-maliciously, connecting to your internal resources within your enterprise. All right, so maybe we have a separate virtual network to handle that guest communication path, and then we can combine that internet access connectivity to some other subset of internal resources that maybe a partner might get access to, or a trusted consultant or a trusted advisor, right? The idea of this compartmentalization provides us the ability to, like I said, on an a la carte basis, provide additional services for, on an as-needed basis, I should say. All right? We know that services on the network are rather complex these days. We have different offerings that include things like voice over IP and hotspot service providers, basic internet access where we have to protect our clients but still provide ease of use and compatibility, and so on. So the network architecture, the architecture, I should say, of this network virtualization has three major components, and this graphic here kind of breaks that down. You've got the access control component, you've got the path isolation component, and the service edge component. Now, if we talk about access control, we're talking about things like traditional security elements, right? Having a VLAN to separate broadcast domains, having access control lists and access control policies, whether they're layer 3 or layer 2, whether they're applied at the port level, at the VLAN level, at the routing level, whatever it might be. The access control list provides kind of a static way for us to filter traffic in the network. We would have things like 802.1x that would provide us the ability to authenticate devices and users. We might run things like MACsec. We might run things like quality of service elements as well, if we're talking about a service standpoint, prioritizing certain types of traffic over other traffic, and so on. So the access layer is that front-end facing layer where policy gets attached and services get attached to service the clients. And we're going to get into some detail in this particular section, as well as some other sections coming up, on how we can handle this with different types of technology. Specifically, we're going to talk about generic route encapsulation, and we're going to talk about virtual route forwarding, which is a pretty important concept. In fact, we do discoveries on both of those topics specifically, which brings us to the next stage, right? What is path isolation? Path isolation often gets considered as a VPN, a virtually private network. We've known path isolation for many, many, many years. ATM, asynchronous transfer mode, did path isolation with SVCs, switched virtual circuits. Frame relay did path isolation with PVCs, permanent virtual circuits. And of course, MPLS, multi-protocol label switching. We also have the ability to do path isolation either with a service provider managed VPN or with our own customer managed VPN technology. Things like DMVPN, dynamic multi-point VPN, or simple IPsec site-to-site VPN using the IPsec protocol suite, or MPLS, either VPLS or virtually private LAN service or virtually private wired service, VPWS, or maybe a layer 3 MPLS VPN. The idea here, though, is that, again, within the cloud, within the service provider network or the internet for that matter, because we may be doing our own VPN, we're trying to isolate and separate our traffic, providing that those three cornerstones of delivery when it comes to security, right? The CIA triad: confidentiality, integrity, and message availability, right? So when we talk about path isolation, that's in essence what we're referring to in this particular case. And then at the services edge, we have lots of different service clusters that we can provide. It could be data center services, it could be remote access services, e-commerce services, it could be internet edge services, and so on. But the idea, again, is that we are responsible as IT administrators to provide a centralizing policy that allows enforcement points whenever it's possible to control and restrict the communication between these different logical partitions. One of the courses that I recently recorded was the SD-WAN course. Go check it out on our YouTube channel. But in that course, I talked a lot about path isolation. We talked about overlay networks versus underlay networks, and you know, transport versus transported, and the idea of creating this path isolation based on that. All right, with regard to path isolation, there's all kinds of things we can do. Again, we can do virtual VRF Lite, which is essentially just virtual route forwarding without MPLS. And in that case, we could do GRE, generic route encapsulation. We could use an MPLS VPN. The main advantage, of course, of MPLS compared to some of these other technologies is this any-to-any connectivity without having to manage a whole bunch of individual point-to-point connections. Certainly, GRE doesn't really provide that. GRE is a point-to-point tunneling mechanism. However, if you implement something like DMVPN, dynamic multi-point VPN, you have the ability to kind of take advantage of multi-point technology in the case of multi-point GRE to make it a little bit more scalable and so on. All right, so generally speaking, GRE is usually considered just a simple point-to-point connectivity solution, but when you're implementing DMVPN, you can get away from that with these dynamic multi-point GRE interfaces, all right? We don't really get into DMVPN in this class. We will see it in the advanced routing course, the advanced enterprise services course, I should say, but we won't get into it in this particular course, all right? So how are policies for security zones enforced? Individually? No, because that doesn't provide the scalability that we need in order for us to effectively manage our domain. It would be like having kind of disparate, separate networks that we have to manage. By groupings, maybe. You know, it is possible to say, okay, well, these groups of services are going to be controlled and managed, and these group of services are going to be controlled and managed separately, but we're going to group those common services together. The answer is, and certainly they are not enforced. We always have policies that are enforced when it comes to security. Centrally is the choice here, right? Centrally is the choice because that's what we talked about multiple times throughout this section here. But the idea is that we want to be able to centrally manage this environment. And that's really where software-defined networking comes into play. And prior to software-defined networking, we had other tools that were available to us to manage our domains effectively. Okay? So again, the idea here is that we are trying to provide transparently the services that would exist in any kind of regular physical architecture, but the idea is that we're trying to do this in a virtual environment so we can scale this and have that flexibility with reduced cost, reduced operational expenditures, and so on. Now, the next thing we'll talk about is kind of that middle block, if you will, what we refer to as path isolation. As the slide here describes, it says path isolation refers to the creation of independent logical traffic paths over shared physical network infrastructure. So this is going to use VPNs, and again, they can be service provider managed VPNs, they can be client managed VPNs, and so on, with various techniques and mechanisms to map different technologies. We can have different layer 2 segments, different transport circuits, but the idea is that we're trying to provide this end-to-end isolation connectivity between different groups of users. Now, if you think about this, when we're trying to segment the network, we're trying to improve the overall efficiency of that network, whether it's how resilient, that's the availability component of our CIA triad, whether the security service is available, scalability is a concern as well, cost is always a concern as well. All right, so the technology that we use to create these virtualized environments really need to include those elements, if that makes sense, right? In other words, meaning that we have to have technology that's going to preserve the resiliency and the scalability, and always, always, always keeps in mind security, right? That is a huge component of this discussion. Let's say, for example, a hierarchical IP network design is implemented. Now that means that you have a combination of layer 3 services, which are routed services, and layer 2 services, which are switching services. Both of these different types of services have to be virtualized, and the virtual domain has to be mapped to the other to keep that traffic segmented. All right, we can do this a lot of different ways, but we combine virtualization of the network devices, which we call device virtualization, with the virtualization of their interconnections, which is what we call data path virtualization. All right, in traditional networks, meaning networks that are not virtualized, high availability and scalability are basically going to be achieved by using some sort of hierarchical and modular design based on that traditional core distribution and access design. All right, and a lot of that hierarchy in that modularity is discussed in all kinds of courses that you see with Cisco, and we reference that quite often. All right, but there are some areas of the network that will benefit from the use of, say, layer 2 technologies like VLANs. That's something that would typically apply to, say, like a campus environment. And over the WAN, maybe MPLS or frame relay or ATM. So a hierarchical IP network is really just a combination of these layer 3 routed components and the layer 2 switched components, which we call domains. Both type of those domains have to be virtualized, and those virtual domains have to be mapped to each other to keep that traffic segmented. All right. Now, virtualization at layer 2, as it says here, not really a new concept, right? VLANs have been around forever. VLAN tagging, ISL 802.1q, all of this stuff's been around for a very, very long time. But now what we need is some way that gives us the ability to extend the logical isolation over the routed portion of the network based on the mappings that we have at layer 2. Path isolation is really kind of just a generic term that refers to this logical virtualization of the transport network. And it can be done and configured in lots and lots of different ways. All right. Virtualization of the transport itself has to address the virtualization of the network devices as well as the connections that connect those different network devices. So again, like I said, we have two options. We have data device virtualization, and we have data path virtualization. All right, and we can kind of see that broken down here. If you look at the device virtualization context here, we can see stuff like Vrf Lite, easy virtual networking, 802.1q or VNet tags for separation. This would be kind of all considered to be somewhat layer 2 elements. With multi-hop environments, we might have Vrf Lite with GRE or GRE traffic. In a multi-hop environment, we also might have MPLS VPNs, and we do MPLS labels for separation, right? Device virtualization, by definition, is the virtualization of the network device. This includes the processors, the processes, the databases, the tables, and the interfaces within that device itself. When you get into data path virtualization, this is the virtualization of the interconnection between the devices. All right, again, as the diagram previously showed us, this could be single hop or it could be multi-hop interconnections. So for example, if we look at this diagram again, the Ethernet link, right, between two switches provides a single hop interconnection, and we can virtualize that with an 802.1q VLAN tag, but frame relay and ATM, those are going to be used to separate virtual circuits and provide data path virtualization. All right. Now, we see in the context of the text here in the courseware, it says here, the goal of a robust network design is to minimize the extent of the broadcast domain and exposure to spanning tree loops. All right, that seems like kind of a basic concept, right? Spanning tree is not something that we can necessarily get rid of completely, but it is certainly something that we need to manage. And maybe we try to design it out of the topology as best as possible, but it's always going to be there. All right. It also goes on to say it is required to translate the layer 2 VLAN to a layer 3 virtual network or a VPN. And this layer 3 VPN has to be capable of supporting its own unique control plane completely with its own addressing structure, routing tables, data forwarding, completely isolated from any other layer 3 VPN. In other words, if I'm running an MPLS layer 3 VPN architecture as a service provider, client A's traffic, even though they might be sharing the same address space, they might be sharing the same services, the same protocols, they need to be logically separated at every level. Their processing, their control plane. Remember, the control plane is the higher level function, if you will, of transport functions, right? It's the BGP, it's the EIGRP, it's the Ospf, it's the routing, all right? That needs to be separate from the other customers so that we can make sure that even though customer A might be using the 10.10.0.0/16 space, and customer B is using the 10.10.0.0/16 space, that those customers are not going to have their traffic commingled, and there's not going to be any chance that traffic might escape or leak into another customer's network. All right, and we do this, by the way, and we're going to get into this in detail. We do this by utilizing tools like virtual routing and forwarding, right? VRFs. All right, and we're going to talk a lot about VRFs over the next couple of slides here. All right, now the last paragraph here real quick. The VRF is defined on a networking device that serves as the boundary between the layer 2, which is the client-side VLAN, and the layer 3 transport network. Typically, that's going to be a provider edge device. It's going to be running, if it's an MPLS network, it's going to be running things like multi-protocol BGP. We're going to be doing implementing the context of route distinguishers and route targets to be able to control that VPN traffic and to be able to identify the clients individually, right? The CE router, the customer edge router, is passing its own private information to the PE router, but the PE router is connected to multiple customers. So that's the point within the network topology that we need to start to create these VRF instances, which are separate routing and forwarding tables for each of the customers. Some of the common protocols that we might see: Ospf, Probably not so much EIGRP. Certainly it's robust enough to be able to handle it. BGP definitely, probably never going to see RIP version 2. But again, you've got your CE router, you've got your PE router, and the idea is that we're trying to send that customer traffic to the provider edge, but the provider needs to be able to distinguish that customer's traffic from other customers without having to dictate to the customer how they need to be able to route. All right, so a VRF instance is compared to virtual routers that are co-resident on a single device, a single physical device. All right, so it's a very, very important concept. Now we go on to say here that with data path virtualization, like I said, it can be a single hop or multi-hop and so on. All right, we talked about all of the different concepts. Now VRF Lite, we'll get into VRF again in one of the future topics here, virtual routing and forwarding. VRF Lite is really in essence just the implementation of VRF instances without MPLS. So you might be using 802.1q trunking to provide connectivity. You might be using GRE or multi-point GRE for multi-hop path isolation and so on. But VRF and VRF Lite are essentially the same thing. It's just whether or not we're using a MPLS transport network or we're not using an MPLS transport network. All right. Again, MPLS is one of the most popular and widely used technologies. Obviously, SD-WAN comes into play here, but if you go back and check out those SD-WAN videos, you're going to find that SD-WAN integrates with these transport technologies because the underlay network is really, doesn't change. It's the overlay network that SD-WAN implements, and that's what provides us the ability to manage the flow of information. All right. In addition, within each networking device, we have multiple planes to virtualize. The control plane is the higher level function. That's your routing protocols, your databases, your EIGRP topology table, your BGP table, anything that's going to be used to make those intelligent forwarding decisions and to maintain a loop-free network layer reachability table, right? Or topology, if you will. All right. So in essence, the control plane is the brains of the device. We have to be able to virtualize that element so that if we have multiple customers, they get their own control plane services based on what their needs are. Okay. Based on what their needs are. At the forwarding plane, this is, you know, the layer 2 data plane, if you will. We call it the forwarding plane, but that's gonna be the virtualization of the forwarding caches as well as the physical interfaces that are used to actually service that data plane function. All right. So you can actually virtualize the control plane and the forwarding plane at different levels. They can map to different layers of the OSI model. So you could have a VLAN aware virtualization where we're virtualizing layer 2 and you only have a single routing table for reachability. So we're not necessarily virtualizing layer 3. I suppose an example of that would be MPLS in the context that you have MPBGP as an overlay protocol to exchange customer routing information. All right, so in the MPLS core, we're not virtualizing layer 3. We're really kind of virtualizing layer 2 with the use of MPLS labels and switching and so on. All right, so you can do that in many different ways. Now, you can also do policy-based path isolation. You can do control plane-based path isolation, and so on. So if I was to kind of give you a little bit of information about policy-based path isolation, it's really just a technique that allows us to restrict the forwarding of traffic to specific destinations based on policy and completely independent of the information that is actually provided by the forwarding control plane. An example of this would be using an access list, for example, to restrict valid destination addresses to particular subnets that might be within the same VPN. That's a policy decision that you're making to restrict traffic flow. Now, these policy-based segmentation options they're kind of limited by two different things, right? First of all, the policies have to be configured pervasively. That means that all the edge devices that represent that first layer 3 hop in the network have to be aware. We also have locally significant information, IP addressing information, and so on, which can be applied to the generic policy, but it still has to be addressed independently, if you will. All right. Because of you have this diverse nature of IP addressing, policies really have to be configured consistently across the board. Building policies based on IP addresses alone isn't really going to scale well. All right, so again, there's very limited application in this particular environment. Another option, like I said, is to do control plane based path isolation, where path isolation, in this case, the technique that we use restricts the propagation of routing information so that only the subnets that belong to a particular VPN are included in any of the VPN-specific routing tables and updates. To accomplish this goal, right, to set up the control plane virtualization, you have to have lots and lots of different control and forwarding instances, perhaps one per VPN. And that actually scales pretty well in most modern networks. VRF is a perfect example of that. A VRF instance is basically just an instance that consists of an IP routing table and then some sort of derived forwarding table, and then interfaces that use those forwarding tables. And I guess we would define things like rules and routing protocols that determine what goes into the forwarding table itself. All right. So we'll get into that in a lot more detail a little bit later on. Like I said, there are many different instances or concepts here. The data path virtualization. Again, we want to focus on whether this is a single or multi-hop technique. I don't know that we'll get into it in a whole lot of detail in this section because it's a pretty robust topic, if you will. I know there's some great documentation on Cisco's website. In fact, if you go out to cisco.com and you search for Path Isolation Design Guide, a lot of this material came directly from that document, and you can see a lot of those particular details. All right. There's a lot of different considerations that you have to take into account. What types of applications are we running in the VPN? Are we integrating things like voice over IP technologies? Voice over IP is not as forgiving as, say, some of our data applications. Is there an overlay design that's part of this overall network virtualization environment, right? And then, of course, we always have to take into account security and security considerations. QoS would be another thing to consider, and so on. All right. So which of the following is a hop-by-hop technique for data path virtualization? Hop-by-hop technique. The only one that's really going to apply here is probably 802.1q. We see that listed here. Again, we'll get into this in more detail, but the idea of hop-by-hop is that the policy is derived and applied to the physical links. Not at the router level, but the links between the routers. So that's why we call this a hop-by-hop mechanism. Multi-hop means that the policy is implemented on the ingress, could pass through multiple routers, and the policy is, of course, applied on the other side as well. So the policy propagates through the network as opposed to the edge of the network or broadcast domain in this particular case. It's really a definition of layer 2 versus layer 3 in this particular case. All right. So let's get into our next discussion, which is virtual routing and forwarding. Now, it says here, by definition, a VRF is an instance that consists of an IP routing table, which derives a forwarding table, essentially a cached forwarding table, interfaces that use that forwarding table, and then different kind of rules and routing protocols to determine what goes actually into the forwarding table. That's kind of almost identical to the description that I just mentioned on the previous slide, right? But VRF comes in many flavors, well, at least a couple of different flavors. It is, in essence, a technology that allows multiple instances of a routing table to essentially coexist within the same physical device at the same time, regardless of whether or not the routing information that's contained in that routing table is the same, right? From different customers or different service providers or whatever it might be. So you might have one or more logical or physical interfaces on the device as well. They can have a VRF, and then those VRFs don't need to necessarily share routes. So the packets that are forwarded between interfaces within the same VRF are isolated from the other virtual routing instances and so on. It's essentially layer 3's equivalent to a VLAN. Because the routing instances are actually independent, we can have the same or overlapping IP addresses without conflicting with one another. All right. In addition, network functionality is improved because the network paths can be segmented without requiring multiple physical devices. All right. Now, the simplest form of VRF was something that we referred to as Vrf Lite. Basically, in this implementation, each router within the network participates in the virtual routing environment in a peer-based fashion. All right, it's very easy to deploy, and it's really applicable to like a small or medium-sized enterprise, or even maybe multi-tenant data centers and so on. But the problem with Vrf Lite is it doesn't really scale to the size that's required by very large enterprises or large carriers, because there's a need to implement each VRF instance on every single router, including the middle routers or the intermediate routers in between. The VRFs that were initially introduced to address this issue was VRF in combination with something called multi-protocol label switching, or MPLS. But VRF really is just massively useful especially to that particular type of environment, because it allowed that isolation, if you will, within the MPLS environment. So like I've said a couple of times already, in terms of Vrf Lite, it's essentially, in essence, the use of VRFs without MPLS. All right? So let's see what they say here in the text. They say that Vrf Lite has the following advantages. It allows for true routing and forwarding separation. We talked about that, right? That control plane separation. We can have essentially the same subnets, the same IP addressing space, but we don't have the concern of overlap, because there's no communication with the devices that belong to different VRFs, unless we've actually explicitly configured that. And then, of course, we would have to be concerned with whether or not there's any kind of overlapping concept. It certainly simplifies the management and troubleshooting of the traffic that belongs to a specific VRF. It's kind of like saying, I've got my voice traffic in VLAN 10 and I've got my data traffic in VLAN 100. That's definitely going to make it much easier to troubleshoot VLAN or the voice traffic if it's not commingled with the data traffic. Same concept here, right? Because in this particular case, we have separate forwarding tables that are actually used to route the traffic or send the traffic to the destination. Different data structures, and we even have our own separate global routing table as well. This means that the overlay network is where we use the global routing table for reachability between the PE routers and the P routers within the cloud, if you will, especially if this is an MPLS design, but it's completely kind of independent of what's happening on the customer side. All right, we could have different default routes. We could actually have, and we might see some of this, we don't really get into MPLS too much in this class, but if we were talking about MPLS VPNs, we could have different service VPNs that different customers are participating in, and they can essentially subscribe to those VPNs, and all we would have to do is establish some sort of routing policy that allows cross-pollination of routes and reachability to those different VPNs. That's where route targets come into play, along with the route distinguishers. All right, so again, this is the main component, right? The VRF achieves the virtualization of the network devices at layer 3, and then they have to be mapped, of course, to their appropriate layer 3 broadcast domains and so on. But, you know, we'll take a look at this briefly. You know, the idea of the exposure in this particular class is somewhat limited. Certainly in the advanced routing and services course, we're going to get into this in a lot more detail, but we are really not getting into this in too much detail in this particular case. All right, just to understand that it's just kind of a general technology that allows multiple instances of routing tables to exist on a specific router. All right, and again, the idea here is that we're trying to increase functionality by allowing network paths to be segmented without using multiple devices. And because that traffic is automatically segmented, it allows us to add a layer of security. So it potentially, although I wouldn't completely agree with this, could reduce the need for things like VPNs or at least cryptographic VPNs to further protect the traffic. All right. So it's basically just like a logical router. But while it's a logical router, it could include many, many different routing tables. For example, a particular VRF instance uses only a single routing table, but we might have multiple VRF instances. All right? And that's what's called upon, by the way, to do the forwarding of the packet based on a set of rules and routing protocols that would essentially govern how that particular packet is forwarded. All right, so the question in this topic is, which of the following options is not an advantage of network isolation with VRF? Uses one routing table that all VRFs use for routing and forwarding. Allows for true routing and forwarding separation, so that's definitely an advantage. Simplifies the management and troubleshooting of traffic belonging to a VRF, that's definitely an advantage. Enables the support of alternate default routes. So clearly the answer here is A, uses one routing table. Yes, we have a global routing table for reachability, maybe across a transport network, but independently we also have routing tables for each VRF and forwarding information for each VRF. So next we're going to get into our next discovery, where we're going to take a look at virtual routing and forwarding, and we're going to do a quick implementation, and then we're going to do have a little discussion about generic route encapsulation. We'll do an additional discovery, and that will wrap up this particular lesson. All right, everybody, welcome to Discovery 15. In this discovery, we're going to configure and verify virtual routing and forwarding. So we're going to implement path isolation using Vrf Lite. No MPLS component for this. First, we're going to verify our existing Ospf configuration on our customer routers, and then we're going to go ahead and deploy VRFs on the service provider router for each particular customer. And then we're going to go ahead and enable Ospf for the ISP router for both customers. That's the protocol of choice in this particular topology. You certainly could use other protocols if you wanted to. We're going to do that for both customers to verify the routing and the path isolation, make sure that that's been successfully configured and implemented. And again, just as always with all of our discoveries, all of the devices are already, they have their basic configuration. We can see the topology here in this particular diagram. So the configuration tasks are broken up into 3 individual tasks. Configure Ospf and on the customer routers, configure Vrf Lite on the service provider router, and then configure Ospf on the service provider router to verify our VRF path isolation. Okay. All routers, again, have their basic configurations in place, their host names, their IP addresses, and again, Ospf has already been configured on the customer routers. So the first thing we want to do is go ahead and verify the Ospf configuration on all of our customer routers. We're going to start with customer A site 1, and we're just going to do a quick show run section router just to make sure that we have the appropriate configuration. So we're running process number 1. We've got a couple of loopback interfaces that are in area 1 and our service provider network side in area 0. And if we go ahead and do that at site 2 as well, show run pipe section router, we can see pretty much a similar configuration except for we got area 2. And again, the backbone is going to be our 172.16.2.0 subnet. If we go ahead and take a look at customer site B, show run section router, similar configuration here. Notice we do have somewhat, I wouldn't say specific overlapping address space, but we do have potentially some conflicting address space here in the 10 subnet. 10.0 is being used on all of these routers. And we'll do the same thing, show run section router, and we can see our Ospf configuration on this router as well. So again, all these routers are configured with Ospf. Each router is advertising its loopback interfaces into Ospf and its link to the ISP router. Area 0 is going to be used between the customer routers and the ISP router, and there are no Ospf neighbor adjacencies presently with the ISP router because we haven't configured Ospf on the service provider router as of yet. Notice that from the customer's perspective, there are no VRFs defined or any kind of necessary routing implementations for the customer sites. All the VRF configuration is actually going to be done on the service provider router, which brings us to task number 2, configuring Vrf Lite on that service provider router. VRF versus Vrf Lite, right? To support multiple customers, and we've talked about this many, many different times, Cisco routers offer the functionality of a virtual router. This is called VRFs, virtual routing and forwarding, and specifically it's called a VRF table. This can be used to store routes separately for different customers. The use of separate tables solves part of the problem, at least, of preventing one customer's packet from leaking into another customer's network because of overlapping prefixes or cross, where we're using the same address space between the customers, but it's still going to allow the sites for the same customer to communicate. All right. Now the VRF itself is going to exist inside of a single router. Typically, the routers need at least one VRF for each customer that's going to be attached to that particular router. So in this discovery, that router is going to be the ISP router. It's already connected to both customers, so it's going to have to be configured ultimately with both VRFs. And then each VRF itself is going to have 3 primary components. It's going to have an IP routing table, the routing information base. It's going to have a Ceph fib, a forwarding information base, which is populated based on the VRF's RIB. And then it's going to have a separate instance or process of the routing protocol that's actually used to exchange the routes between the CE routers, those are the customer edge routers, that need to be supported by the provider edge, in this case really just the provider router, because we only have one, which is the VRF. So customer A and customer B are both using Ospf in this particular case. By the way, that doesn't have to be the case. Your customer can choose whatever protocol they decide that they want to use. In this case, it happens to be Ospf routing. The ISP router has to maintain a separate routing table for each customers. Now, VRFs are typically configured along with something like an MPLS VPN, but VRF doesn't require the use of MPLS. And as I've mentioned a couple of times in my lecture, deploying VRFs without MPLS is simply known as Vrf Lite, and that's really the focus of this particular discovery here. All right, so the first step in this configuration is to go into the service provider router, and we have to create the Vrf instances. So we're going to go into config T, IP VRF, and we're going to say cust A, and we're going to say exit, and then IP VRF cust B. Now these names don't really have any general significance. They just simply represent a placeholder, if you will, for the VRF configuration. Now the name is going to be referenced in other locations. So in that sense, it is important to understand what that is. But as far as picking the name, it's a somewhat arbitrary value. You can pretty much pick whatever you like. Again, I like to use all caps because that will stand out in the configuration as you're going through and doing the configuration and verifying operations. All right, so now what we need to do is we need to apply these virtual routing instances to the interfaces. Customer A VRF needs to be applied to Ethernet 1.0 and 1.1, and the customer B VRF needs to be applied to 1.2 and 1.3. So let's go ahead and go into interface Ethernet 1.0, and we're going to say IP VRF forwarding cust A. Now make sure that, of course, you assign the VRF based on the one that you created with a case-sensitive name. Also notice that in this particular case that the IP address was removed. This happens because the interface is being moved from the global routing table to a VRF routing table, so we have to reconfigure the IP address on the interface. So we're going to say IP address 172.16, 1.18, 255.255.255.240 in this case. All right, so very, very simple configuration. Let's go ahead and do the rest of the interfaces. Interface Ethernet 1.1, we're going to go ahead and put that in A. And for this IP address, it is going to be 2.18. All right. Same subnet mask. And then we're going to go into interface Ethernet 1.2, which is customer B. Obviously, you want to make sure you don't mix that up as well. This one's going to be 1.34 with the same subnet mask. And then interface Ethernet 1.3, that's also going to be customer B, and this is going to be 2.34 in this particular case. Then the addressing is really simple. It's basically router 1, router 1 and 2 in customer A, and router 1 and 2 in customer B. All right, so the addressing obviously may not be the same in your environment if you're implementing this, but nonetheless, it's pretty easy configuration. Now, one of the commands that we can use to verify VRF is just simply show IP VRF, and that will tell us which customer or which VRF exists, what interfaces are participating in a VRF. Pretty simple output here. We can also do a show IP VRF interfaces, and we can see which interfaces are participating in which VRF. And we can also do a show IP route. Now, if I do a show IP route, all I'm going to be looking at in this particular case is the global routing table. Now, notice in this case, we don't even have connected or local routes because we've already assigned all of our active interfaces on this platform to VRF. So if I do a show IP route, VRF cust A, for example, and I want to see the connected routes, then I can see that the interfaces 1.0 and 1.1 are assigned to that interface. I can do the same thing for customer B. I can see those interfaces are attached. So again, the show IP VRF command gives us the currently configured VRFs, the interfaces that are associated to each of those VRFs. The show IP VRF interface command gives us the interface IP addresses and the line protocol status, which is very useful. The show IP route command gives us the global RIB, the global routing information base. Obviously, again, we only had 4 active interfaces on this router, so no interfaces showed up in that global RIB. Had this been maybe a PE router that then had some interfaces that were connected to some P routers, we would see some of those interfaces, those P connections in our global RIB, because those would be the connections that go into the provider network. All right, and then we did a show IP route VRF to display the individual VRFs. All right, so on the ISP router, I want to do a quick connectivity test to the directly connected routers. Again, I always recommend to do this because before I start to set up routing and start to overlay all these other more complex configurations, I want to go through and I want to make sure that the basic functionality is there. So I'm going to do a ping VRF in this case for customer A, and the destination I'm going to ping is the peer router that I'm trying to reach in this particular case. The ARP process caused the first ping to fail, but the rest of them went through. Same thing with the 2.17 address. We're .18, the customer sides are .17. And then I also want to do the same thing for customer B. So let's do customer B in this case. Oops. And that is 1.33, excuse me. And 2.33. And we should get a response in both cases. All right. So all the pings are successful. By default, if I didn't specify the VRF, the ping command is going to go ahead and use the global routing table. But since the ISP router is configured for VRFs, we use the ping VRF command. And we can do that with extended options as well if we need to. So our third and final task before we do our final verification is to configure OSPF on our ISP router. Now we could do this for IPv6, we could do OSPF v3, address family configuration. I mean, the fact that we're running a VRF doesn't really change the ability to configure these other protocols in different ways, with different protocol stacks, all the different elements that we talked about with regard to the protocol, the function of the algorithm, the function of the protocol, doesn't really change just because we're running a VRF. It just basically means that we're isolating that functionality within the VRF, which is kind of nice because we can actually now go ahead and customize the protocol per VRF. So for example, if I want to configure OSPF, let's say router OSPF 1, let's do 100 in this case, just to make it match what they're doing in the lab. Customer A, so we're assigning this OSPF process to the VRF customer A. We're going to specify a router ID of 0.0.0.100, and then we're going to put in our network statements, 172.16.1.16, 0.0.0.15, so that's the kind of the ISP connection to the top customer A router. And then we see we get an adjacency in that case. And then we want to do our 2.16 subnet as well. Remember, it's a 240, so we are using a 16 block wildcard mask. Again, you could reference the specific IP address if you wanted to. The network statement's going to be entered pretty much how it would normally be entered, as you're configuring OSPF. But we should expect to see the adjacencies come up. Let's go ahead and now do the second process. Of course, you would want to make sure that you have a unique process ID in this case. And we're going to go ahead and do customer B. The router ID here is going to be 0.0.0.200. And the network is going to be 172.16.1.32 with the same wildcard mask. That's going to go into area 0. So again, we should see an adjacency come up. And then 2.32, we should see an adjacency come up. All right. So that means now that each VRF now has its own unique process ID. You don't have to configure the router ID. It's still going to grab the router ID based on normal processes, but only from the interfaces that are participating in the VRF. And it's going to be the highest loopback or the highest physical IP. We like to set the router ID just to promote stability, right? Now, as far as the OSPF router configuration goes for VRF, it's identical to traditional OSPF routing. The only difference is that we're assigning the process to a VRF in this particular case. All right, so we saw all of our adjacencies come up. Now we can use some other commands to verify operation. One of the first verification commands that we can do is show IP OSPF neighbor. And we can see that we have our neighbor adjacencies. This is interesting because we don't really see necessarily the relationship between the neighbor adjacencies and the VRFs in this particular case. Now, we do have the option, I believe in this iOS, to filter that. No, we don't in this case. It would be right here. I believe, if I'm not mistaken, there are some OSPF options that you can kind of look at adjacencies outside of, within a particular process. Certainly if I did show IP OSPF neighbor, and I look for, I'm trying to think if it's in, under this option, if I specify detail, trying to see if we see any reference to the VRF in the detailed information. We don't. So I remember seeing at one point there was an option, and I can't remember if it was in kind of a newer version of iOS or an older version of iOS, where we were able to see the virtual information, but I'm not seeing it here. So in any event, as long as you can kind of correlate interfaces, you can do a show IP VRF and kind of match the interfaces based on the neighbor relationship. So we know that these two are in VRF A and these two are in VRF B. All right, customer A and customer B. So let's do a show IP protocols. And in this case, let's go ahead and use, I know you can do this. So this would be useful as well, right? Because we can maybe possibly identify and correlate this to the neighbor table. But it's really the same as the standard show IP protocols output. It just allows us to verify the router ID, how we're participating in the OSPF process. I could do the same thing for customer B. We can see the router ID of 200 in this case, and so on. Now, the router IDs themselves do not have to be unique across VRFs because, again, we're not really exchanging anything across the VRF. But in general, it's best practice to kind of always make sure that your router IDs are unique across kind of any multiple process configuration with EIGRP. You just don't want to take the chance that you're going to have some sort of instability in the OSPF configuration. Show IP route, VRF, customer A, and we should see some inter-area routes in this particular case. Remember, these are the ones that are coming from Area 1 and Area 2. ISP is actually participating in the routing in this case, and it's actually acting as the backbone router for both of these VRFs. So it's going to have those inter-area routes from those different areas. All right. If I take a look at customer B, I should see a similar output, those 4 loopbacks in router Area 2 and Area 1. All right. So we have our adjacencies with all 4 of our customer routers. The show IP protocols command allowed us to verify that. And we could use the VRF to kind of filter out those details. And that shows us the router ID and the VRF information for the networks being advertised. And then each routing table contains only the routes within the specific VRF. Customer A routes are isolated, customer B routes are isolated, and so on. So I can do my pings now. Ping VRF customer A to 10.0.1.49, which is one of the loopbacks. And I can also ping 1.17, which is another loopback, 1.50, another loopback, and then I should also be able to ping 1.33, which is another loopback. For customer B, I should be able to ping 2.49. See, 2.49. I should be able to ping 2.17. I'm trying to think the other ones. 2.50, I believe, is one, and 2.33 is the last one. All right, so all the pings are successful, which means that we've essentially configured VRF. All right, now if I go to the customer site 1 router and I do a show IP route Ospf, we can see the routes as if they're native Ospf routes. Remember, we're not running in this particular case VRFs on the customer side. We're only running VRFs on the ISP side to ensure that we have that separation for each customer. I could do a ping here, for example, to 10.0.1.50. I'm going to source that from loopback 0. That works great. 1.33. Source that. And then I can do 2.49 as well. 2.49. That one fails, right? That one should fail because that's the other customer. Remember, the 2 addresses are the other customer, all right? Which, you know, basically says, hey, we don't have any reachability, even though that those routes exist on the service provider router. So if I go to customer B site 1, show IP route Ospf, same result, right? Same result. We see the 2.32, we see the 2.50 subnet, and I do my pings. I don't have to do a VRF ping here too, because again, we don't have the VRF here. And let's do source loopback 0. And let's try our 2.33. And let's try our 1.50, which should fail. All right. So pretty straightforward exercise, pretty basic configuration. You can have lots and lots of VRFs. You can have all kinds of mixed configurations, if you will. One VRF might be running static routing. The other VRF might be running EIGRP. Another VRF might be running BGP. You know, it just depends on, you know, what kind of routers are connected and what your overall goal is with the route distribution. So we'll wrap up this exercise. We're going to get into a discussion about generic route encapsulation. And then we're going to do another discovery where we're going to talk all about GRE and implementation of GRE, which is also a fairly simple configuration. So we'll see you guys in the next section. So in this topic, we're going to talk about kind of just an overview, if you will, of GRE, generic route encapsulation. Again, a lot of the topics in this particular course are not necessarily deep dive topics. We're going to get into a lot more detail on these things. When we do our discovery, of course, I'll try to expose some more details through the use of Wireshark captures and looking at PCAPs and stuff. But the idea here is just to get a general understanding of what these protocols are. When we go into the advanced routing course, we're going to spend a lot more time talking about these particular topics, all right? Now, as the bullet points state here, GRE is one of many different tunneling protocols. That's absolutely true. There are multiple tunneling protocols that are available. There's IP and IP tunneling, there's IPv4 and IPv6 and V6 and V4 tunneling, there's L2TP tunneling and so on. Probably, I don't know, 10 or 15 different tunneling techniques that you can use. Now, GRE rides right on top of IP. Specifically, it's protocol 47. The GRE header is relatively small. It's only 4 bytes. But we are adding an additional transport IP header. So the overall overhead for GRE is 24 bytes. Now, that's a very lightweight tunneling protocol compared to some of the others that might exist. The nice thing about GRE, though, is it allows us to pretty much tunnel anything, any kind of protocol that we want. Multicast traffic, broadcast traffic, unicast traffic, as well as other protocols and so on. It really is data agnostic when it comes to what can be transported in the tunnel. Now, it does by definition provide a secure path for transport, but it does not provide encryption, all right? So it is, as you can see from the diagram here, we have a couple of different elements, right? We've got the underlay network, the transport protocol, which could be just basic MPLS routing, or it could be just site-to-site routing. Maybe we're running some, just basic internet connectivity. But that transport protocol is just basically how we get the data from point A to point B. In this particular case, from tunnel interface A to tunnel interface B, or whatever it might be. We've got the carrier protocol. In this case, the carrier protocol would be GRE. And then we have the passenger protocol. The passenger protocol is the protocol that's being carried by GRE itself. And again, a lot of flexibility with what we can actually encapsulate inside of GRE. So we have this 20-byte IP header, which is essentially used for transport, right? That's the header that's going to allow reachability between the outside interface of this device and the outside interface of this device. We've got our GRE header, which basically is indicating to the routers, hey, you don't need to analyze any more of the packet payload information because it's GRE. In other words, any router in between would say, well, I don't need to see what's inside the passenger packet because I'm not using that information to make forwarding decisions. All right, so the GRE header contains flag fields, a protocol type field. We'll see this, by the way, when we do our discovery. I'm going to do some Wireshark captures. We'll take a look at the details of a GRE header. We'll break that down. There could be a checksum involved. You could potentially be running some sort of a keying and sequencing, of course. But this is a key right here. GRE does not encrypt traffic. So oftentimes we'll implement GRE with some sort of other kind of IPsec overlay, if you will, that provides that IP security, which provides confidentiality, integrity, and so on. Look at the note here. It says GRE was developed by Cisco and to encapsulate arbitrary packet types. Arbitrary meaning basically any packet type. It was defined in RFC 1701, GRE RFC 1702, GRE over IPv4 2784, and so on. All right. Actually, the original GRE RFC was 1701. Excuse me. GRE over IPv4 was 1702, and generic routing encapsulation was 2784. All right. So the tunnel is going to support different headers, like for example, the passenger protocol. That's what we're carrying inside, and that's what's being encapsulated, right? And like I said, with GRE, unlike some other tunneling protocols, we have no limitation as to what can actually be included in the payload. Anything could be included in that payload. We have a carrier protocol, GRE in this case, and then we have our transport protocol, which typically is going to be v4, but it could be v6. It doesn't really matter. That's what provides that end-to-end reachability to establish connectivity between the tunnel endpoints. All right. It is a stateless protocol because it runs directly on layer 3. So there are no flow control mechanisms. There is no strong security, as we mentioned. And the GRE header, along with the additional IP transport header, is going to provide 24 bytes of overhead. All right. So you would actually have to adjust, and we'll talk about this in the discovery, the MTU. We don't have to worry about the MSS, that's layer 4, but we will have to worry about the MTU so we're not generating fragmented datagrams, if you will. All right. Now, just to give you a little bit more information, because I think this slide that Cisco provided is a little bit anemic, so I want to do a little review, and then I also want to get into some of the tunneling techniques, and we'll see this in the discovery as well. We already know that GRE encapsulates the data packets. It redirects them to a device across some sort of transport network that then de-encapsulates them and routes them to their final destination. All right, this is going to allow the source and the destination routers to operate as if they have a virtual point-to-point connection with each other, because the outer header that's applied by GRE is transparent to the encapsulated payload packet. All right, so for example, GRE tunnels allow the routing of routing protocols like RIP or Ospf or EIGRP over a public domain, which would never normally be allowed, because first of all, multicast is typically preferred, if not required, for these protocols to operate. And plus, in order to peer EIGRP routers or Ospf routers, they have to have point-to-point connectivity, right? At least over a layer 3 domain. All right. So GRE tunnels can now encapsulate that multicast data stream and then transmit that over the internet or over some other transport network, and it would look like those devices are directly connected. Like I said, GRE, the primary RFC that we use for most GRE is 2784. That kind of obsoletes those two other earlier RFCs that we talked about, 1701 and 1702. And Cisco, of course, supports all of the facets of 2784. All right. So we have a tunnel source router. It encapsulates a payload packet for transport through the tunnel itself to some sort of destination network. That payload packet first gets encapsulated inside of a GRE packet, and then the GRE packet is encapsulated in the delivery protocol. The router that's actually performing the role of the tunnel remote router, right, the destination, if you will, extracts the tunneled packet, forwards the packet to its destination. All right, and that's basically the process that we're talking about. Data is actually routed to the system, to the GRE endpoint over routes that are actually established in the routing table. All right, and we'll see this in our discovery. You can configure those routes statically, you can learn those routes dynamically, and so on. But whenever a data packet is received by a GRE endpoint, it's always going to get de-encapsulated, and then it's going to get routed again based on that inner packet information to its final destination. As I mentioned before, GRE is entirely stateless, so that the endpoint of the tunnel really doesn't contain any information about the state or the availability of the remote tunnel endpoint. All right, so if I have a device that's acting as a tunnel source, we cannot really change the state of the tunnel interface to down, and I'll describe this a little bit more in detail when we go through the discovery, if that destination is not reachable, I should say. All right, now we can apply filtering to these GRE tunnels. We can apply quality of service to these GRE tunnels, all kinds of different options. Now we are going to get into a lot more detail about the protocol specifically. The implementation is really, really simple. Create a couple of tunnel interfaces, put those in a common subnet that doesn't necessarily have to be routable, have your public IP facing your public facing interface, specify in your tunnel interface the tunnel source, the tunnel destination. You don't even have to specify the encapsulation method because the default is GRE, and the rest is history, right? There are some caveats and some gotchas that you need to be aware of, and we'll certainly go through that as we go through our discovery. Okay? So which of these options are the two main GRE characteristics? Is it IP protocol 47? Yes, it is. Right? Specifically, it states that here. We'll see that in our discovery. So that's one of the choices. GRE utilizes encryption. GRE utilizes encryption ciphers. No, it doesn't. Right? You can add an IPsec overlay, but that's going to be independent. DMVPN does that, not by default, but you can set up DMVPN to add IPsec as part of the overall implementation. Certainly not protocol 43. It allows routing information to pass between connected networks, or it denies routing information from being passed between connected networks. We know that it allows routing information to be passed. All right. I don't like the term connected networks. I would say reachable networks, because the term connected kind of sparks the idea that these are directly connected networks. They don't have to be. Right? As long as the transport network allows reachability between the tunnel destination and the tunnel source, they do not have to be connected to each other. All right, everybody, welcome back. We are in discovery number 16, which is the final discovery of this group, or this lesson, if you will, configuring and verifying a GRE tunnel. All right, pretty basic discovery, not a whole lot going on here, but we're going to go through the steps just so you can kind of see the basics of how GRE is configured, how the tunnel's set up, and so on. So I'm going to walk you through the configuration, the verification, and the usage of GRE, generic route encapsulation, specifically the tunneling, and our transport network in this particular case is IP. Now it could be anything else if we wanted it to be. R1 and R4 have some loopback interfaces, and R2 and R3 are completely unaware of those loopback interfaces. They are in the 172.16.0.0/16 space. Those are going to exist on router 1 and router 4. EIGRP is already configured on router 2 and router 3 for the 10.0.0.0/8 prefix. And the tunnel interfaces haven't been configured yet. Part of our demonstration here is to configure one of those, or to configure those tunnel interfaces. Once the tunnel interfaces are up and operational, then we're going to go ahead and verify connectivity between the 172.16 addresses on our loopback interfaces. So we're going to basically configure GRE on R1 and R4, and we're going to enable Ospf over the tunnel. EIGRP is used as our transport protocol, but we're actually going to enable Ospf on the loopback interfaces and on Ethernet 1.1 on router 1 and router 4. That would allow us the ability to communicate. All right. As always, all the devices have their basic configurations in place, including their host names and their IP addresses. This network here is the 10.10.1.1 subnet or 1.1 address. The loopback on R3 is the 10.10.13.1. This interface here is 10.10.1.2. Our tunnel interface addresses are going to be 172.16.1.1 over here and 172.16.99 over here. And then we're going to have our 99.2. And then we're going to have, excuse me, I apologize. We're going to use the same subnet for the tunnel interfaces. I got them mixed up here a little bit. The loopback interface here is going to be 172.16.1.1. The loopback over here is going to be 172.16.14.1. Our tunnel interface subnet is 172.16.99, with router 1 being .1 and router 4 being .2. That's the general configuration that we have, and we'll walk through this as part of our configuration as we go through each step. All right. Now, in the first few steps of the discovery, our goal is to go ahead and verify the status of the network as it's been set up. And this is always kind of what you want to do when you're dealing with any kind of implementation. Start by verifying basic functionality. Start by verifying basic usability. Because it doesn't make sense to go ahead and start configuring advanced functions, show IP route, if the basic functions aren't working. So we do see that on router 1 we have a static route to the 10 subnet. In fact, the entire 10 subnet. We should have something similar on router 4 as well, a static route to the entire 10 subnet. Now keep in mind that's my public transport. Normally this route would be handled by a default route, right? Typically sites are going to have a default route that points towards the internet. In addition, we would probably not be using a private RFC 1918 address block for our basic public domain transport. But again, this is just for demonstration purposes, and we're going to go through the process of kind of verifying everything. Now, if I do a show IP protocols, I can see router 1 and router 4 are not running any routing protocols right now, but I should be able to ping the 10 addresses. So I'm going to ping 10.10.3.2. That ping is successful. If I go to router 2 and I do a show IP route, I can see that I do have an EIGRP route to the 13 subnet here, as well as the 10.10.3 subnet. And that's how we're getting that reachability. On the internet, maybe it's BGP, maybe the ISPs are sharing prefix information through BGP, maybe it's static routing, whatever it might be. But the idea is that we have at least end-to-end reachability from a transport perspective. The 172.16 subnets are not routable, at least not as of yet, because we haven't configured GRE. So R2 is running EIGRP, it's peering with R3. They're going to be aware of the entire 10/8 address space within the topology, but R2 and R3, as you can see from the routing information here, have no visibility for the 172.16/16 prefix. Again, if I do a show IP route here, I don't see the 172.16 prefix here either. All right, so something to something to consider as we start to do this configuration. All right, so the first step is we're going to implement GRE tunneling. Now, generally, there are essentially 4 or 5 basic steps to setting up GRE tunneling. The first is to configure a tunnel interface. We do that from global configuration mode, and we simply specify interface tunnel, and then give it a tunnel ID. And I'll show you what options we have for tunnel IDs in a little bit. Then we would typically specify the tunnel mode. Now, in this particular case, our tunnel mode is going to be GRE over IP. I'll again show you different tunnel mode options that you have based on the configuration that we're going to apply. I'll use the context-sensitive help and give you some ideas of what other options you might have. We don't actually need the tunnel mode GRE IP command because that's actually the default. We're also going to configure an IP address for the tunnel. Now, this address does not have to be public. It does not have to be routed over the transport network. The whole point of the tunnel interface is to provide an encapsulation endpoint for the encapsulation and the de-encapsulation of the GRE traffic that's going to pass over the transport network. So we have our passenger protocol, which is the traffic for the 172.16 subnets. We have our underlay, which is the transport network. And we have our tunneling protocol, which is GRE, which is the overlay. The address that we're specifying here is the IP address for that overlay network, not the underlay network. We're going to specify the tunnel source, which can either reference an interface or a IP address, and then we're going to specify the tunnel destination. All right. Now, this is the minimum GRE tunnel configuration. All right, at a minimum, we have to specify a tunnel source and a tunnel destination, and we have to provide an IP address for connectivity over the tunnel interface. At each end of the tunnel, we have to use symmetrical reachable addresses. All right, so we could use loopback addresses if they are routable and reachable, but in our case, we're most likely just going to use the external addresses, or quote-unquote the external addresses of the router itself. So we're going to go into router 1 in this case. Remember, we're tunneling from router 1 to router 4. We're not tunneling router 2 and router 3. This is essentially the internet. So the tunnel source and the tunnel destination is going to be router 1 and router 4 respectively. All right, so let's go into router 1. We're going to go to config T, and we're going to create interface tunnel. And you can see here we can create quite a few different interfaces. This is an arbitrary number. It's also locally significant to the router. It doesn't really matter that the tunnel interface matches on both sides. We're going to say IP address of the tunnel. In this case, we decided to use 172.16.99.1 with a /24 prefix. We're going to go ahead and say the tunnel source. Now, you'll notice we do have the ability to specify an address, but we also have the ability to specify interfaces. So we can say fast Ethernet, Ethernet, loopback interface, port channel interface, all kinds of different options here. In our case, we're just going to go ahead. Let me do a quick show IP interface brief. Oops. And we're going to be using our quote-unquote outside address. Now, to kind of equate this to what you're going to see in the real world, this would typically be our service provider facing interface. So normally this would be some sort of public address, which is routed across the internet and is reachable from the other side. All right, so it's a little confusing in this example because we're using RFC 1918 address space in both directions. Also notice here the tunnel is up physically, but the protocol, the line status is down, indicating that the tunnel is not functional. That's mainly just because we haven't specified a tunnel source and a tunnel destination. So just keep in mind, we're using the 10 network as our internet, so that's something to consider, all right? So our tunnel source is going to be 10.10.1.1, and our tunnel destination is going to be that other quote-unquote public IP on router 4, all right? Now, notice as soon as I do this configuration, the line status of the tunnel goes up. I haven't configured the other side of the tunnel. There is no mechanism in place to actually verify the functionality of the tunnel. You would have to use some other mechanism as a keep alive mechanism or some other way to verify the status or the operation of the tunnel. All right, the line protocol came up immediately once I configured the tunnel source and tunnel destination. All right, so I've only entered 3 commands on the tunnel interface: do show run interface tu0. And you can see it's a very simple configuration. Where's the traffic coming from? Where's it going to? And what is the IP address of the tunnel? So now I'm going to go ahead and do the same thing on router 4, kind of a mirrored configuration, if you will. Interface tunnel 0, IP address 172.16.99.2 with a mask of 255.255.255.0. Tunnel source, in this case, is going to be 10.10.3.2, and then our tunnel destination is going to be the 10.10.1.1 address. Tunnel destination, 10.10.1.1 address. All right, so we should see the tunnel come up from this side. Now at this point, I should be able to ping the 172.16.99.1 address. Try that again. Because the tunnel is actually functional. All right, now while I'm doing this, let me go ahead and go into my packet capture mode. And I want to start to capture those datagrams that are going back and forth, because I want to show you that those ICMP echo request and reply messages are encapsulated using GRE and the transport header for the 10 subnets. All right, so let's go ahead and do that ping again. And I'll come back to Wireshark here and pull up any one of these messages, and we can see the encapsulated datagram. So here is our outside packet header. Here is our inside packet header. All right, so this is the actual passenger protocol, which is the ICMP data. This is the transport header, right? This is what's allowing me to get across the transport network. So this is the tunnel source, the tunnel destination. These would be publicly routable addresses that the internet would recognize, or whoever my transport network is would recognize, to be able to route this traffic. We can see that it's got a protocol identifier of GRE, so the receiving router knows, hey, this is a GRE encapsulated datagram, so let me go ahead and check the GRE information to see how I should process this data. Now, there really isn't a whole lot here. I'm not going to get into the specific flags, if you will, for GRE, but one of the important concepts is this protocol type, right? Because now, essentially, we're saying, all right, we've encapsulated this data. Is it IPv6 that we encapsulated? Is it ARP? Is it, 86DD for IPv6, 0806 for ARP? In this case, it happens to be hex 800. So now the router knows that received this datagram. Okay, I need to now send the packet up to the IP process to process the inner packet header, which is what allows me to get to those 172.16 addresses. All right, and then this is just our standard ICMP data. So it's a relatively basic process, right? Encapsulation occurs, GRE, we create our outer tunnel packet, our transport packet header, and that's what allows us to route. All right. Now there are other ways that we can verify GRE operations. We're not finished with the configuration yet because we still have to add the routing overlay on top of this to be able to define reachability. But we could do a show IP interface brief and look specifically for the tunnel interface. We can do a show interface tunnel. We can do a show IP route. You know, the basic stuff that we would use to verify reachability. All right. So if I go, for example, on router number 1, and I execute the command show IP interface brief tunnel 0, we can see the information, right? Up, this is the address, this is the tunnel interface, and so on. All right, so the status and the line protocol for the tunnel interface show up. We would do the same thing on router 4, show IP interface brief tunnel 0, and we would see similar information. All right. We can also do a show interface tunnel 0. We can get some more details here, right? We can see the tunnel source and the tunnel destination. We can see the protocol. I forgot to show you that actually, so let me do that. Interface tunnel 0. And one of the things that we are able to specify in this case is the encapsulation type, tunnel mode, I should say, which is really basically the encapsulation type. And notice we have so many different options here, right? Do I want to do an IP and IP tunnel? Do I want to do an IPsec tunnel, IPv6 tunnel? Even GRE, I have a couple of options. I can do IP transport, or I can do an IPv6 transport, or I can set up some sort of multi-point GRE interface, which is typically used for things like DMVPN. So lots and lots of different tunneling options. These other tunneling options are not related to GRE. These are just completely different types of tunneling methods that we have. All right. The default tunneling mode, though, let me get out of config mode here. Show interface tunnel 0. The default tunneling mode, it is a tunnel, and it should say here how we're doing the tunneling. Let me do a show IP interface, TU0. And we should see, I'm not sure if it's going to be on this output or the show interface output. It's probably going to be on the show interface output. Show interface TU0. Show interface TU0. And we do see the tunnel source and right here. All right, tunnel protocol and transport. The tunnel protocol is GRE. If it was a snake, it would have bit me in the face. But the tunnel protocol is GRE, and the transport is IP. Again, the other option with GRE would be IPv6. Okay. Now, if I take a look at the routing table on router 1, the other thing you'll notice is that the tunnel interface shows up as a connected and local route. So it's a virtual interface, but it is a connected interface. All right. So all the traffic that is destined for the 172.16.99 subnet goes into the tunnel interface. All right. So we did that ping. We were able to ping. I can try to ping from this side as well. 99.2. The ping goes through. It's successful because the encapsulation is taking place. All right. So from R1 to R4, the packet of 172.16.99.1 going to 99.2 gets encapsulated like we saw in the Wireshark capture with that secondary IP header. In this case, the source IP of the packet for that outside IP header would be 10.10.1.1 and 10.10.3.2 would be the destination. All right, R3 and R2 didn't really know that the other packets were embedded because they're just using that outer packet header to make their forwarding decisions. All right. Now, the next step then would be how do we define reachability to the loopbacks? Because you can see here we don't really have any other routes except for this static route and our locally connected routes, which means I'm not going to be able to reach that loopback on the other side. Now, this is where I could decide if I want to do a static route to the tunnel or if I want to do some sort of dynamic routing process like EIGRP or Ospf. It's entirely up to you as to what you want to do. All right. We're going to go ahead and set up Ospf. I'm going to start with router 4, and we're going to go into router Ospf 1. And we're going to say router ID. We don't need to necessarily do this, but again, it's best practice. And then we're just going to add the tunnel interface and the loopback interfaces to Ospf, and we'll just do a flat single area implementation here. All right. And then I'm going to do the same thing on router 1. Config T, router Ospf1. And again, it's a really basic configuration, right? Router ID 0.0.0.1, network 172.16.0.0, 0.0.255.255. It's extremely important, though, and we should get an adjacency here. It's extremely important that you make sure that you route to the tunnel interface, not the physical interface, because you might end up creating a loop and then your tunnel traffic will not pass correctly. So now if I do a show IP route, and I can see now that I'm learning those Ospf routes from the tunnel interface. Not the physical outside interface, but the tunnel interface. All right. And of course, we're going to be able to ping. Let me try it here, 172.16.4.1. Sure enough, we can ping. If I do a show IP Ospf neighbor, I have a full adjacency over the tunnel interface. And really, if I do a show IP Ospf interface, I can see that the tunnel interface is running Ospf. Where is it? Right here. It is actually defined as point-to-point. It does assign an arbitrary cost value to that interface. That is something you could change. There really isn't, if I do a show interface tunnel 0, we don't really have a bandwidth. There is a calculated bandwidth for the interface and a calculated delay. But again, this is just arbitrary numbers. Well, I wouldn't say arbitrary, but it's defined in the iOS, but they don't really mean anything because this is not a physical interface. Okay? Now, that being said, show IP Ospf interface. If you look at the Ethernet interface, it actually has a cost of 10, whereas the tunnel interface has a cost of 1,000. It's just something to keep in mind. It's not related to the interface that we're referencing in our configuration with regard to where the tunnel source is and the tunnel destination is. So if I go back now to my Wireshark capture, you can actually see that the hello packets are encapsulated inside of GRE. Now imagine that in this case, router 2 and router 3 are the internet. These are service provider routers that have no idea that we're running Ospf, but guess what? Our Ospf traffic is being sent over this GRE tunnel to be able to terminate that Ospf neighbor adjacency. And there could be 10 routers in between, 100 routers in between. Our only limitation is the number of hops based on the time to live of the packets being generated. Now, the only other thing that I might recommend as really a best practice, even though we can see the tunnel is functional here, make sure that the IP addresses are not used anywhere else in the network. Each tunnel interface gets an IP address within the same network as the other tunnel interface. It doesn't have to be a /24, it could be a /30 or an IPv6, a /126 or 127. But keep in mind, GRE is an encapsulation protocol. So we do probably need to make some adjustments on the overall packet or MTU and MSS. So if I go into interface tunnel 0, a couple of other best practice configurations would be an IP MTU 1400 and then IP TCP MSS adjust MSS, excuse me, and we would probably set that to 1360. These are the maximum transmission unit length and maximum segment size. Most transport MTUs are about 1500 bytes. And we have added overhead because of GRE, and we have to reduce the MTU to account for that extra overhead. Setting the MTU to 1400 is common practice. It's going to make sure that unnecessary packet fragmentation is kind of kept to a minimum. As you can see, again, that's not something, by the way, that has to match on both sides of the tunnel. in order for it to function. Now you could, in addition, add IPsec if you wanted to. GRE is an encapsulation protocol. It doesn't perform any encryption. So we could secure the GRE tunnel with IPsec, creating obviously a point-to-point GRE tunnel without any encryption. Kind of risky if you're sending your traffic over the internet. So IPsec could add a layer of encryption, if you will, which gives you that confidentiality, security, and whatnot. Now, I'm not going to go through the process of adding encryption to this tunnel. That's not part of the configuration, but the first step, you would set up your phase 1 policy. So you might do like a crypto ISAKMP policy 1 and specify your encryption and your hashing and your authentication method, your group, Diffie-Hellman group, and your lifetime. Then you would set up your pre-shared key with your partner by using the crypto ISAKMP key. Then you would create your IPsec transform set, which is basically your phase 2 policy. Crypto IPsec transform set, maybe we'll do AES 256 with SHA HMAC for message integrity or hashing and so on. The IPsec mode, by the way, if you do it, should be transport mode. And then we would go in and create a cryptographic profile, global mode crypto IPsec profile. We would match the security association lifetime and then match the transform set. And then we would simply apply the IPsec configuration to the tunnel interface. Now, we didn't set up everything else, but basically you would just come in here and say tunnel protection, IPsec, and then you would reference whatever profile you created in this particular case. Obviously, I haven't gone through the whole configuration, but that's going to add encryption on top of it. Certainly in our CCNP security classes, we'll talk about that as part of that process. All right, so that's really the whole exercise. There's really not a whole lot to it. You can pretty much transport anything over this tunnel at this point. But which 2 commands could I use to verify the status of the tunnel interface? Well, how about show IP interface brief, right? Or show interface tunnel, right? And look at the tunnel interface. Maybe it's tunnel 0. I suppose you could do show IP route if you are using the routing table to verify reachability, which could only be accomplished if the tunnel interface is functional, right? Or you may see it as a connected or local route or in the routing table. So there's maybe a couple of different answers to that, maybe a couple of different ways we can get to that. All right, so we're going to wrap up this discovery. Thanks for joining me. We'll see you guys. We're going to wrap up this whole lesson actually now with our summary challenge, and then we'll see you guys in our next discussion later on. So taking a look at our summary challenge for this lesson here, which hypervisor is used with almost all collaboration applications? That would be VMware ESXi or vSphere, definitely. All right. We talked about that in our initial section here. Which of the following options is a logical container that holds all the resources that an operating system requires for normal operations, graphics adapter, memory, processor, networking, and so on? That would be our virtual machine, right? The guest is a term that we often use to describe the operating system specifically, but the virtual machine is what is going to house all of those resources. And I went through in our first lesson and kind of walked through the Gns3 virtual machine and the Windows 3.1.1 virtual machine. What is the command sequence to configure a GRE tunnel interface on a Cisco router? We want to specify a tunnel interface. We need to specify a tunnel source and a tunnel destination, and the tunnel interface is going to have an IP address. Now, in this case, I'm trying to see here, certainly this would not work because we're not specifying a tunnel destination. This would not work because we don't have an IP address. So I guess the question is, what is the difference between this one and this one? Here we specify a tunnel source as an IP. The tunnel destination is an IP. Typically, the tunnel source is going to be an interface. So I'm going to go with this is probably the better choice because we're actually specifying an egress interface. We're assuming that anyway in this case. An egress interface as the tunnel source. And then the tunnel destination is here. The only other thing I would say is, you know, they're using RFC 1918 addresses, but we're going to have to assume reachability in this particular case. All right. Which network virtualization architecture component transports traffic over isolated layer 3 partitions? All right. That would be path isolation. Path isolation allows us to transport traffic over layer 3 devices. All right, because that's what we're talking about in essence here. We're talking about the layer 3 transport path, the routed path, if you will. All right, which of the following are the headers that are added to an existing packet by GRE? We got the 4-byte GRE header and an additional 20-byte transport header for IP. By the way, this would change if you were doing GRE over IPv6. You'd have a 40-byte header instead of a 20-byte header. But we're talking about IPv4 in this case. Which of the following options are the benefits of server virtualization? Can we share physical resources? Yeah, I would say that. Underutilization of CPU? No, we'd like to have optimal utilization of the CPU. Hardware resource consolidation? Yeah, I could see that, right? We're consolidating the memory, the CPU, the physical hard drive space. So we would need less physical resources. And we would need, because we need less physical resources, we would need fewer cooling requirements as well. Which IP protocol number defines GRE packets? Protocol 47. This is UDP. And protocol 50 is ESP, Encapsulated Security Payload, and protocol 51 is AH, Authentication Header. You can go out to IANA.org and just search on protocol numbers, and you can see all the protocol assignments. 17 is UDP, 6 is TCP, and so on. All right, so we're going to wrap up this lesson. We'll see you guys in the next lesson.